Hello everyone, this is Professor Ma and this is the section on derivatives. Okay. Uh, we the topics we're going to go through are the slopes, what we mean by a slope at a point, and then we're going to talk about the difference quotients and we define what derivative is going to be. And then we will do three basic examples, the algebraic calculation using the definition, difference quotient definitions. Okay. We know what the slope of a straight line is, and now we want to define what the slope of at a point on a curve is. At each location, the curve goes up and down, and then we define very reasonably say the slope at a point, for instance, at a point P will be the uh, slope of a tangent line at a point P. Okay, so like over here, the point P has obviously then the interval has positive slopes with respect to the curve on the curve y equal f of x, and the point N we will have that it has negative slope. And so these having positive slope or negative slope at a point on a curve, therefore has a geometric meaning whether you are going uphill or going downhill. You can imagine that's a silhouette of a hill. And we're going to use that analogy quite a bit. Okay, so the slope at a point P, we can calculate it, and the formula will come up with, it's called a derivative. Okay. And where does it come from? It comes from the difference quotients. So let me remind you the difference quotient again. Okay, so suppose I have a point, just uh, x f of x. So I go point x, and f of x is the height. And I have its neighbor, x plus h, um, for some small distance h, and that its neighbor has a point correspondingly on the curve. Its coordinate is this x plus h and f of x plus h. We're going to connect a straight line, then we're going to measure the slope. Okay, and the slope, of course, is the difference delta y over delta x, and the difference in the y coordinate. Now I'm going to write everything in function notation. Then it looks like f of x plus h minus f of x. That's delta y. That goes in the numerator. And then the denominator is the delta x is of whatever the h, the horizontal distance between the numbers. Okay. Then the slope, of course, is a quotient, delta y over delta x. Okay. And this is the difference quotient. It is the slope at the point of a line connecting x point at x base at x to its neighbor whose points based at x plus h. Okay, and here's the second degree calculation. For example, and if I move the point x over a little to x plus h, okay, and that point coordinate over this point will be f of x plus h, and then if I want to calculate the slope, the difference quotient, the formula come out to be is a quotient of the difference between the f of x and f of x plus h, divided of course by the h which is the same as from here to this h. So this is the algebra need to be calculated. Note, f of x plus h is plugging x plus h into this formula, and it comes up with all these. It's x plus h squared minus twice x plus h. Okay? And this is the second degree algebra, which is first type of algebra that we should know how to do, because it's just a practice, good practice. For one thing, we cannot know what the answer is going to be. The answer is always going to have three terms on x and h and a number. Okay. So this we call also the expansion of x plus h squared, and remember this comes out to be x squared plus 2xh plus h squared. Okay. So that's the algebra you have to watch out for over here. And everything clean up, and notice the h can be a factor from the top, will cancel the h, and then this is the difference quotient simplified versions, okay, for these second degree equations. And again, this is the algebra which you should know, and a lot of homework practice on second degree. Okay. Now, of course, to find what the slope is at the point x for the red line, is that we take these, the black line, that is the chord over here, we'll calculate difference. I'm going to move the tips, and we're going to move the tips along the line, and it gets closer and closer. In other words, I'm going to let h become smaller and smaller, okay? So move the point x plus h closer and closer to x, and that's a limit of procedures. Okay, but when limit h go to 0, this black line basically coincide with a tangent line. Then the limit of the tangent of these tangents of those black line is the slope at point x, f of x. Okay, and so therefore the definitions of derivatives is the following: f prime is the derivative. We call this a derivative, okay, and we'll call it f prime. We define to the limit of this difference quotients, if it exists. Okay. And in the last problems over here, this is f the difference quotient, so we will, to find the derivative, all I have to do at the last step is to take the limit, let h go to 0 for these simplified difference quotients. Of course, when h go to 0, these become 2x minus 2. Okay, and that's what here. F prime of x is 2x minus 2 from the last problem. Okay. Let's know a couple of things. F prime is a function. It's a formula in x. Secondly, this formula in x is derived from the original f. We'll do all the difference quotient, then do algebra, we'll come to f prime. Hence, we call f prime the derivative, derived from. From what? From the original f. What does it do? Oh, it gives you the slopes of the tangent line at each point along the curve. And wherever x is, you plug in the x, then it will give the slope of this line. So if this x is 2, you plug in 2 in here. 2 times 2 is 4, minus 2 is 2. Then it tells you the slope is 2. Okay, if you plug in 3, you get 4. Then they tell you the slope at 3 is 4. Okay. So let's say 3 is here. You plug in over here, and then they tell you the slopes at 3 is 4, etc., etc. Okay, so it's a derived formula, and the formula tells you the slopes along this curve. Okay. And for instance, if I want to find the slope at x equals 1, you plug in the 1 at the point 1, 1. You know, this is the point correspond on the curve if tangent is 0. Slope of the tangent 0, so it's horizontal. And that has significance about the curve. That means in this case, it's the bottom of the curve. the smallest number. There are many notations. We write f prime of x. Okay, we also, if this is y is equal to f of x, then f prime of x is a derivative, or we also write dy dx. This is the actually came from this dx. Okay, and why two different forms? They each have their advantages in the calculation process. For instance, the dy dx notation is a lot more advantageous. Use that notation to do calculations. F prime, a lot of times, a lot more advantageous to do chain rules. So you don't have to write as many things. So each one has its own advantage and its drawbacks, the notations. Okay. So all these means the same thing. If x squared, f of x is x squared minus 2x given here, the f prime of x is derivative. It's same thing as df dx. Take the derivative of f with respect to x dx. Well, we will talk about that dx in bottom, so it will be more later on. S sometimes capital with the operation derivative with respect to x of f, and sometimes put a prime, and all these means the same thing. Okay. And there are three algebra we go through, and the first ones use the linear definitions of prime using the difference quotient definition. That is, we calculate the difference quotients, okay, and simplify these. The algebra, I'll let you check the algebra. Remember, for second degree or third degree, for actually for any polynomial, and we concentrate on the second degree. One simple fact is, after you finish the simplification, the h will be canceled. The aim over here is to cancel the h in the denominator. What? Because we're going to let h go to 0. You cannot have the h become 0 in the denominator. So we have to change this formula look different to remove the h in the denominator, causing troubles for the limits. In this case, it canceled. Okay, so it actually clean up and cancel. Then we take limit as h go to 0, and it's when h go to 0, then of course these middle terms become 0. Then the limit is going to be depending on what x is. It's going to be minus 4x plus 3. That is its derivative. The derivative of the second degree equation. A reminder. Every second degree equation works out like this. Works out like what? When you get to here, you get xh, h squared, h. The h can be pulled out. It will be three things out there, and each one has an h in it. Okay, and that's not difficult to see because the original formula is in here. It's going to get canceled. The only thing left will be things with h on top. And that's what all three things are. And h comes out and cancel. And that's what the algebra tricks. You have to use it to, it's a good exercise to use it to practice the algebra. The second one is a fractional. And this is basically fractional algebra revisit, okay? First, write the difference quotient. What does the difference quotient look like? It's plugging x plus h over here. So plugging the x plus h over here, minus 1. And minus the original with x there. Okay, before with x plus h, subtract without the plus h. Then the whole thing sits on top of h. This is what difference quotient is. Okay. And this is a complex fractions. So this is the exercise in complex fractions. How do we reduce these? Multiply top and bottom by the least common multiple of the two denominator. These two denominator, okay, I'm going to find the common denominator between them, and which is the product, and multiply one on top, one below. And at this point, do not do anything to the bottom. Okay, if This is a general thing in mathematics. If I have a fractions, the denominator is factored, leave it factored, unless for some special reason we need to expand it. So leave the bottom factors. In other words, the entire algebra to be carried out is up here. Okay, and that simplified pretty fast because the purpose of the common denominator multiplication is when I multiply these canceled. But if I multiply that one, the second one canceled. So what I wind up with is this. And then no cancellation up and down. You need to expand the top. And again, what's left on the top has a h as a factor, which will allow us to remove the h. And now I can take limit as h go to 0. Okay, the second step of the derivative is let h go to 0. After you do the difference quotient, then the second step is let h go to 0. And when h go to 0, this h disappear, become nothing. So I get minus 2 divided by x minus 1 squared. And that's the derivative of 2 minus 2 over x minus 1. Okay, so f of x is this one right here. And its derivative is this one. And then we'll do a simple square root. Okay, and this is the difference quotients. And how can we change it so we can remove the h on the bottom so we can take limit? Conjugate. Okay, so what? Well, so just to clean up the top a little bit. And the conjugate multiplication remove the square root. Okay, so I will have the square root of this square and pop the square root out. And this square and pop the square root out. And so what's left is this. Make sure you have a parenthesis here. Okay. And then this become minus 2x plus 3, and then, oops, and the 2x minus 3 and 2x plus 3 cancels it. So leave you 2h on top. That h cancels and leaves a form now in the difference quotient. The original difference quotient look like that. I cannot take the limit h go to 0. But in this one, yes, I can let h go to 0. That's the second step for derivative. And then when h go to 0, I get this disappeared. And I get the two square root, same square roots added twice. So I get 2 and then cancel the 2's and I get that. Okay. So these are 3 different type of algebra. You know, the square ones, the simple fraction ones, and the square root. And 3 different basic algebra we keep using. And it will come back again, the 3 different type of algebra. Here's an example of geometries. Okay, it's kind of says a lot of setting context and blah blah blah. Basically, what it's saying is this: we have this curve, y is equal to minus 2x plus 3x1. Okay, and we're going to put at a point x equal to 1. Well, x equal to 1, plugging 1 minus 2, 4, 2, 1, 2. So at point 1, 2, we're going to draw a tangent line. And basically, we're asking where is the x-intercept on the tangent. Okay, so that's strip away all these words, and that's what the picture is. So, in other words, I need a slope for the tangent line, and I know a point it passes through. Okay, and we can calculate the slope of this as below. Okay, the derivative of this, it we calculate it. I'll leave it to you to calculate the difference point. It's going to be these. So when we plug in 1 for the slope at prime at 1 means I want a slope at 1. I want to here's 1. Here's 1, 2, and the slope is this number f prime of 1, which we calculated plugging 1 in here, is minus 1. Okay. Well, then once we know a point and a slope, that I can find the tangent line. Okay. And I'm using the formula y is equal to mx minus point x0 plus y0. The point is x0, y0. Okay. And future, we're going to replace the slope m by derivative. That's f prime at x, right? So then this will be, oh, by the way, it's x0. Okay, because I know where it is. It's at x0. Okay. So in the future, these will be the equations of the tangent line, the actual equations. Okay. And we're going to use this formula over and over again. That is the slope, point slope form. Because we find the tangent line, slope, now we know the point, boom, I know the tangent line. So here's a tangent line. So where is the x-intercept? Y0 x-intercept 3. Okay. That's it. Bye-bye. Until next time.